Welcome back. Today is the second session of quantitative literacy. Last week we talked a little bit about quantitative thinking and I gave you some background in my statistical philosophy. And this week we're going to do a really rapid introduction to statistical inference. I want to guide you through some of the most common types of tests and models that you might see in a piece of quantitative work so that you're a little more familiar with it if you ever want to use it or if you encounter it in an article or a book. So let's get started. We're going to begin in a very specific point in the statistical research cycle. So you may remember this diagram from last week. This week, we're going to be focusing on statistical inference. And we remember that statistical inference is that key piece that brings us from the sample world back into the population world where our question lies. So we started with a question about the population. Since we were unable to sample that entire population, we took a sample. From that sample, we can compute estimates, fit models, compute summary statistics, but we're not done because with just these things alone, we are still living in the sample realm. So we need to use statistical inference to move back to individuals. And one of the fastest and quickest ways to do that is to use a confidence interval. So what is a confidence interval? So using the data that we collected from our sample, we can compute a point estimate. So let's say that we want to estimate the average income of people in a certain population. So we sample a bunch of people, we ask them their incomes, and we can compute the sample mean. That would be our point estimate. But we know that that is almost certainly not the true number, right? It could be a little bigger, it could be a little smaller. So what we do is we pick two numbers, we compute two numbers, one larger and one smaller than our point estimate to form the upper and lower endpoints of our interval. The distance that each of those points is away from the point estimate is called the margin of error. Well, what's the margin of error? We'll come back to that in a second. But for now, just remember that each endpoint is margin of error distance away from the point estimate. And the total length of this interval, so the distance between the upper and lower endpoints, we call this the width of the confidence interval. And that will come back when we talk about how to interpret intervals. Okay, so this is the general idea of the confidence interval: a point estimate, an upper endpoint, and a lower endpoint. So let's dig into margin of error. So we know that the value that we've computed is certainly not the right value. So what could impact how right or wrong our estimate is? And these are the three main things: the variability of the data, the sample size, and the confidence interval. So how does variability of the data impact the quality of your estimate? Imagine you have a population where pretty much everyone has the same income, right? Maybe it varies by a couple $1,000s, but nothing too bad. Well, then no matter what sample you take, right? No matter which people end up in your sample, every sample looks the same. All the data generally looks the same. And so the estimates always look the same. However, if you have a highly variable population, so you have some very, very wealthy people, some people with much lower incomes, then it would be possible to get some samples that have all people from the low income side of the spectrum and samples that have people only from the high income side of the spectrum, in which case the data in those samples looks very different, which means you could get very different types of estimates. So high variability of the data in the population leads to high variability in the samples. But we can counteract that a bit by the sample size. So even if I have a population where my variable of interest has very high variability, if I'm able to take a large enough sample, then every sample will still more or less look like every other sample. So imagine a crazy situation where you're able to sample everyone except one person. Then no matter which one person gets left out, it's basically the exact same group. So that's an extreme example of how sample size can help you. But it gives you a good insight into the idea. So when we're computing the margin of error, we have the variability of our data. In general, we call that standard deviation. And we divide that usually by the square root of the sample size. But in general, you have variability, which the bigger it is, the more error you have. And then we divide that by the sample size, because the bigger our sample size gets, the less our error, the more our error should go down, the smaller it should be. Okay, so the last thing is what we call the confidence level. So sometimes we need to be more confident in our results than we do in other times. So if you're dealing with clinical trials, if you're dealing with firing rockets where you need really, really high precision, you don't want to take any more chances than you have to. And so you need really high confidence. There are other times where we can be a little less extreme, where we're okay with a little more error. Maybe we are okay with having a lower confidence, and so we can use a smaller number. Where this number comes from, you don't need to worry about it now unless you want to read more into it, but we would just multiply the ratio of the variability to sample size by our confidence level. And this number is our margin of error. So I've used the word confident a lot in the last 2 minutes, and a very natural question should be, confident in what? Because confidence, to be confident, has a very kind of everyday meaning, but we are talking about confidence in a quite mathematical sense. So the confidence level of a confidence interval is the success rate of the method you use to compute the interval. It's not your confidence in the interval itself. So let me give you an illustration. Let's say we're sticking with this average income. The average income of a fixed population, so no one's born, nobody dies, no one gets a new job, that's a fixed value. So if I had every single person's income, I could compute this true value. And that number lives on the number line between minus infinity to plus infinity. That's a fact. I don't know what this true value is, but it is fixed in this number line. But since I don't know it, I go out and I get a sample. I compute an estimate and its corresponding interval. And you can see here, this interval crosses that value of the true parameter. So the truth is caught in the interval. But there's no reason I needed to get that exact sample. I could have gotten a different sample, which would lead to a different point estimate and a different confidence interval, or a different sample, or a different sample, or a whole bunch of different ones. And sometimes I could even get a sample where my confidence interval doesn't contain the truth at all. Do you see how in this orange confidence interval, it doesn't cross the true value? The true value is not inside this interval. But most of the time, it works exactly the way one would hope. And indeed, in this case, I computed a bunch of 95% confidence intervals, and 1 out of 20 times I get a sample, or 5% of the time, I get a sample that gives me an interval that doesn't contain the truth. But 95% of the time, whatever sample I pick will contain the truth. And that's where the confidence is. It's my confidence in the method I used, not confidence in the interval I compute. So maybe the most important thing, how do I interpret it? So you may not be interested in computing your own confidence intervals, but you will almost certainly, if you read any quantitative work, you're going to see a confidence interval. So the first thing is, were the assumptions met? And I can't go over all the assumptions for every possible confidence interval, but in general, people should always mention whether or not assumptions are met. If they don't, it's a fair place to push back, but you can always look them up yourself and check to see if you agree that the assumptions were met. The other thing are, how wide are the intervals? So remember, we talked about how the length, so the distance between the upper and lower endpoints, is the width of the confidence interval. And the reason we care how wide they are is because if they are too wide, they're basically useless. So imagine if you're applying for a new job and, someone says, oh, the salary is somewhere between $1 and $1 million. Incredibly accurate. Okay, that's a very true statement, but it's not informative in any way because that interval is way too wide. It's the same with confidence intervals. So we don't want them to be too wide. And if you think back to the formula for margin of error, when you have a wide interval, it means your margin of error is really big, which either means that the variability is super high, the sample size is very small, or the confidence level that they're trying to use is extremely, extremely high, more likely a combination of some of those three things. So how wide are the intervals? Is it narrow enough that it actually provides meaning? The other thing we want to look at, this is important whether you're reading how someone else is talking about their confidence intervals or if you're describing your own. The sentence we use is, we are 95% confident that the true value of the parameter is between lower endpoint number and upper endpoint number. What we don't say is there is a 95% probability that the true value of the parameter is between the lower endpoint and the upper endpoint. And I'm going to show you a picture of why this 95% probability statement is not true. So you've computed a confidence interval. You have your point estimate, you have your lower endpoint, and you have your upper endpoint. And that interval lives on a number line. And so does the true value, right? The true value is fixed and unknown. So let's put some numbers on here to clarify this. Once you have a fixed interval, right? You've taken your sample, you've computed the interval. The true value is either inside or it is outside. There is no probability anymore because there's nothing random. The randomness, the probability, happens before the process starts. So before you begin collecting data, there is a 95% probability that the true value will be in the interval that you get. But once you take your sample, it's either in there or it's not. There is no probability left. So it's a small thing in the wording, but scientifically, it does make a difference. So that's confidence intervals. And that is pretty much the first step anyone will take to try to move themselves from the sample world back to the population world. The other thing that you may have seen before is hypothesis testing. And hypothesis testing can feel very daunting when you're first learning it. And sometimes I think that's because we make it a little too mathematical. And there is a lot of heavy mathematics that underpins it. But I think if you take it from a philosophical view, it's much easier to wrap your head around. So the general idea behind hypothesis testing is actually quite simple. So you start with, I have a belief. Then I gather more information. And then based on information, I have to decide whether I should update my belief to some specified alternative, or do I not do that? And I just choose to keep my current one. Okay. In general, this starting belief, we call this the null hypothesis. Okay. Typically, this will be the thing that is opposite to the claim you want to test, because it's not fair to have your starting belief be the belief you want to test. So the null hypothesis is that starting belief. This updated belief, this specified alternative, we call this the alternative hypothesis. In notation, you might see this labeled as H1 or HA. They both mean the same thing. It just depends on what field the person was trained in. So let's talk about error and power. So we can think about all the outcomes of a hypothesis test using a 2x2 grid. So there is a reality. Either your null hypothesis, your current belief, is correct, or it's not, right? It's only one of the two things. There's also the decision of the test. You either decide to update your belief. You forego your current belief in favor of some alternative belief, or you don't. You fail to reject your current belief and you decide to keep it for now. And this leads to some situations which would have a correct outcome, such as when your null belief is true, your current belief is correct, and you decide to keep it. But if your current belief is correct, you may, because of the test, decide to reject it. That would be a wrong decision. It would also be wrong if your current belief is not true, but you decide to keep it. And of course, it would be right if your current belief is not true and you decide to update it. And we actually, these situations are so important, we do give them names, or I give them names. So If your current belief is true and you decide to keep it, that is a win. That is a success. But that's kind of easy. You kind of started at the finish line. You already had the right belief and you weren't able to get any false information, right? You weren't able to be persuaded to give that up. That's kind of an easy thing. The other success, I call this the more difficult success, because you're starting with a false belief. Your current belief is wrong, and you were able to go out into the world and find information that was convincing enough for you to give up your current belief. And if you think about just everyday life, what's easier? Is it easier to convince someone that the opinion they currently have is true? Or is it easier to convince someone that their current belief is false and they should think something else? It's exactly the same with hypothesis tests. We also name our types of errors. So if you decide to update your belief when your current belief was actually true, we call this a type 1 error. And I bet you can guess what we call the second one, type 2 error. These are very obnoxiously named. They are not in reference to anything meaningful about the type of error. So if that stresses you out, don't worry about the type 1, type 2. There is some symbols that we use, some notation that can help clarify these things. So specifically, we have what's called our significance level of our test. That we denote alpha, and alpha is the probability of a type 1 error. So it's that probability that you update your belief when your current belief was true. You rejected your current belief even though it was true. And that's the probability of a type 1 error, and we call that alpha. We want that to be quite low in general because it's a little embarrassing to start with the truth and then give it up. We also have a notation for the probability of a type 2 error. We call that beta. And then perhaps the most important quantity to learn about when you're learning about hypothesis for the first time is something called power. So power is computed to be 1 minus beta. So it's 1 minus the probability of type 2 error. So more precisely, power is the probability of being able to make the hard right choice. And what was that hard right choice? That is when you reject your null belief, you reject your current belief in favor of an alternative when your current belief is wrong. So what is your ability to find enough evidence to convince yourself to update your belief when indeed you should be updating it? So that's rejecting the null, given that the null is false. And a good question to this is, well, what affects power, right? Ideally, we would want power to be 1, right? We'd want the probability to be 1. I want to always be able to give up my current belief if my current belief is wrong. But that probably won't happen, so I want to make it as high as possible. So what might make power low? And there's 4 main things that do this: sample size, effect size, data variability, and type 1 error. This might sound a little familiar if you're thinking back to the confidence intervals we just talked about what affects margin of error. And the way I think about power, while all of these things mathematically pour into power, I like to think of it through an analogy of a window. So if making the hard right choice, let's say it's the ability to look through and spot something through a window, kind of like an I Spy game. Your sample size is the size of the window. So what's easier to look through, a giant picture window or a tiny peephole? So if I have a larger sample size, I have a larger window to look through. It's much easier to see. The effect size, in my analogy, would be the size of the object I'm looking for. So if you imagine you're looking out this window, if I'm asking you to look for a mouse on the ground, that would be very hard. If I'm asking you to look for an elephant, that would be much easier. It should be easier to find enough evidence to convince you, yes, there's an elephant outside, than it might be to convince you, oh, there's a mouse outside. Data variability works in this context exactly the way that it worked before, but for me in this analogy, it's how clear it is or how foggy the window is. So if variability is low, then it's a very clear picture through the window. It's very easy and precise. And even if the window was very small, because it's so clear, I can easily see through it. But if the data variability is very high, my window is very foggy, having a larger window could be helpful. Imagine if this was very foggy, you could still see there's a sky above. Maybe you could make out some of the colors, right? They're still helping counterbalance each other. But there's also this problem of the type 1 error. So this one is maybe less intuitive, but type 1 error, remember, what is that? That's when you reject the null hypothesis. You reject H0 when the null is true. And look at what power is. Power is also rejecting the null hypothesis, but when H0 is false. So what would be the easiest way for me to minimize type 1 error? The easiest way for me to minimize the probability of rejecting the null when it's true would be to just never reject the null. Right? If I never reject the null, then I certainly never reject the null when it's true. And so I have probability 0 type 1 error. So if I force my type 1 error very, very low, I'm basically saying you don't get to reject very often. And you only get to reject when the evidence is overwhelmingly strong. So in the idea of the window, the type 1 error tells you somewhat how long you get to look through the window. Do I get to sit there for an hour and really pick apart what I see? Or do I just get maybe half a second to glance outside? Okay, that's the idea. Sample size, size of the window, effect size, the size of the thing I'm looking for through the window, data variability, how foggy is the window, and type 1 error is how long I get to look out the window. And power, again, it's a very mathematical object. If you want to do an actual power analysis, there's a lot of coding you need to be able to do. But this metaphor is a good way to get at its importance and the things that affect it. And understanding power now, I would say every day, is becoming more important. More and more journals are requiring power analyses. They're requiring people to state their power, and they're right to do so. So the general consensus is the minimal acceptable power of a test should be about 85%. That's considered acceptable. There was a paper that came out maybe a year or two ago. It was a meta-analysis of political science papers. And they found that the median analysis for the tests in the, I think, 2,000 papers they looked at was about 10%. And that was quite a shock in the political science world, and has really, I think, encouraged the need for really good power analyses. So if you want to do quantitative analysis, if you're wanting to do hypothesis testing, I think spending time to really learn power would be a really good use of your time. Okay, so that's all good and well, but how do I interpret the results? So maybe you find yourself needing to run an analysis, you find some code online, or you have a friend who helps you write some code, and you get a bunch of output. Somewhere in your output, there's going to be this thing called the p-value. And to interpret your results, all you have to know is if my p-value is less than my alpha, my significance level, then I reject my current belief, I reject the null hypothesis in favor of the alternative. P-values, I think, are another one of these places where there can be a lot of misunderstanding about what it is and what it is not. So by its strictest definition, the p-value is the probability that a different sample from the same population could provide even stronger evidence than you currently have against the null hypothesis, assuming the null hypothesis is true. So let's think about an example here. So let's say you think that the average income should be $50,000. Okay, fine. And let's say you compute that the average income is $100,000 for your sample. And what this is saying is you want to know what is the probability that a different sample could give me even more evidence, so even a higher estimate than the 100,000 I have, okay? And if that's a very easy thing to do, meaning that probability is very high, then you're probably not too far away from the true average, right? But what if that number is very, very small, right? There aren't many samples that could give you even more evidence than what you have. Then that means something very special. It means that in a world where the true average is 50,000, you were super, super, super unlucky and happened to get just one of the less than 5% of samples that give you this really high average. And in that moment, you have to make a decision. Either the null belief is true, the true average is 50,000, and you were crazy unlucky, or your sample isn't that special. And the reality is that the alternative hypothesis is actually more likely to be true. And you're not far away from the 50,000. You're actually much closer to some alternative truth. And we talked about this in the last session. One of the things we have to believe in statistics is that rare events are rare and kind of that we're not special. And so if that probability is very, very small, if the likelihood, right, is very small that I could get something even more extreme, then I say I'm already so far away from that null belief. Either I just got really unlucky, or I'm actually in a different world. I'm not in the world where this null is true. I'm in a world where this alternative, it's much more likely for that to be true. So if that was a little too overwhelming, don't worry about it. Focus on if p-value is less than alpha, reject the null hypothesis, okay? So I want to show you a couple common, very popular hypothesis tests. That would be the t-test, the ANOVA, chi-squared test of independence, difference of proportions, and the f-test. If you're new to hypothesis testing, I would start reading here. These are the ones you're most likely to see in any write-up, regardless of what field or what year the paper was published. But perhaps more importantly is what you should do if you ever encounter a new hypothesis test. And I think there's 3 questions you need to answer. Step 1, what is the test's purpose? Every hypothesis test was uniquely and specifically crafted to do something very precise. And you need to make sure that it's doing the thing that the author is telling you it does, or the thing you want to do. Secondly, what are the hypotheses? So part of a hypothesis test is that the null and the alternative, or at least their format, will be pre-specified. You don't get to just choose anything you want. So what are the null and alternative hypotheses? And then third, what are the assumptions? I cannot emphasize this enough. Every single quantitative method is built on some type of assumption. And it's important that we make sure those assumptions are met, because the computer will always give us output, but that output may not always have meaning. And indeed, it is less likely to have meaning when assumptions are not met or if they're weakly met. And we need to know how much we can trust what we're reading. And we'll touch more on that next week as well. So that is the basis of hypothesis testing. Again, we went very quickly through here. There is a lot more to learn. There is a lot more detail and nuance to be had, but today we're just going for broad strokes, and I think that was an okay introduction. So the last thing that, if you're interested in statistical inference, you need to know is linear models, and specifically linear regression. Linear regression is an incredible tool used in basically every field. And the general idea is that you have some outcome variable that you want to model. Okay, you want to know what influences it, what makes it greater, what makes it smaller. And that outcome, whenever you build your model, you're going to have some signal. The signal is the thing that affects the outcome. But that signal is always imperfect, so there's a little bit of noise around it as well. And because linear regression has been used in so many fields, was developed in parallel, we also get a lot of overlapping terminology, which can be very frustrating on the one hand, because you have all these different words that really mean the same thing. But on the other hand, it's an incredibly good signal that this is a good place to spend your time because a lot of different types of people care about it. So this outcome variable Y, some people call it just the Y, some people call it the dependent variable, some people will just say the DV, other people will call that the response variable. The signal portion, right, these predictors, some people will call them independent variables, the IVs, some people will call them a predictor variable, they'll call it the X, they may call it a covariate. That's popular in the statistical community. And this noise part, sometimes it's called error, maybe the epsilon. Some people will call it the residual. It really depends on where the person was trained. But in general, we're going to get a model that looks like this. My outcome is equal to some average value plus the effect of some other variable. So my variable, my independent variable takes on some value. It has some effect B1. I add that to the average value of my Y. And of course, life's not perfect, so we have a little bit of error. That's the general idea. As you start to learn more about regression, you learn you don't need to have just one independent variable, one covariate. You could have 2, 3, 4, 5. And this is simple linear regression. There are much more advanced forms of regression. So this model could also look a lot more advanced as well. But in general, if you see something like this, it's a regression. So interpreting regression results. So we're going to do this using an example. So imagine you have a theory that the number of times per week that a college student goes out is negatively linearly related to their GPR. So this is a graph of some data. On the x-axis, we have the number of nights out per week the student goes. So if they don't go out at all, that would be a 0. If they go out every night, that would be a 7. But most people fall somewhere in the middle. And then GPRs range from 0 to 4. And if we look at the data, there does seem to be some kind of downward slope, right? And indeed, they have already put this regression line here, which is a little bit of cheating at this point. But it does seem that as number of nights gets bigger, the GPR is going down. That is, we're trying to model to figure out what is the slope of this line and what is this intercept here. So what would be our model? GPR, that's the outcome variable, this is our dependent variable, is equal to the average GPR of the whole sample plus the effect times the number of nights out. So this is the effect of the nights out variable. We multiply those together, and then we add that to the average, add a little bit of error, and we get the GPR. And there is a hypothesis test associated with these regressions. And what we have is maybe we want to test this hypothesis. For us, we want to test, is the effect of nights out negatively, so that's less than 0, equal, or is there no effect? So there's either no effect, meaning if this is 0, all of this goes away. So there's no effect of nights out. Or this number is negative, so that as number of nights out goes up, the GPR goes down. So this would be, the current belief is there's no effect, nothing happens. The alternative is the belief we want to test. Okay, so if you're looking at output either from code or maybe in an appendix or in a journal article, if someone has fit a regression model, they're going to have what's called a regression table, and it will look something like this. There may be extra columns, but in general, you will almost always see these. The first thing you're going to see is the constant, that's your intercept. Coefficient, these are your point estimates. So this is our best estimate of what the true intercept is. This is the standard error of this estimate. This is a t-value that is used for a hypothesis test, and this is the p-value of that test. And I'll tell you what that test is in a second. Same thing for nights out. This is the name of the variable. This is our estimate of that effect. This is standard error of this estimate, and this is a t-value. Now these p-values, the p-values you see in a regression table, are for a very specific test. And it is the test of whether or not this number is equal to 0 or not equal to 0. Okay. It is not the hypothesis test we were talking about earlier, which is it equal to 0 or is it less than 0? Because being different than 0, you could be less or you could be greater, right? So there is a nice way that you can manipulate these p-values a little bit to get the p-value for that test, but we're not going to get into that now. You can look that up later. But in general, if this number is less than 0.05, then we say, hey, in reality, this number is not 0. There is an effect. So 0.002 is less than 0.05. So we say, I need to reject the null that this number is 0, and I say it's actually this. And it is indeed negative. So it seems that we have good evidence that our theory is true. So the fitted model, all right, if we replace all of those B's, B0 and B1, with the numbers from this table, is the average GPR is equal to the group average minus 0.239 times the number of nights out the student goes. But of course, this signal, right, is not exactly equal to the truth, so we have a little bit of error. Not too bad. But how do I interpret this? What does this number really mean? And for simple linear regression, the way you interpret this, the way you can show yourself, is by thinking about the difference between someone who goes out some number of nights per week and someone who goes out one more night than that person. And if we do a little bit of algebra, what we see is that for this person who goes out one more night per week, their average GPR is the average GPR of someone who goes out one night less. You see, this is exactly equal to this, minus this number. So this means that we expect that the average GPR, that for every extra night out someone goes per week, we expect that the average GPR decreases by 0.239. So for every additional night out, we decrease the average by this amount. That's the basic interpretation for simple linear regression. So there's a lot more to learn about regression, but the great thing is, because it is such a popular tool, there are so many books and tutorials and short courses and notes that you can take. And what I would really encourage you to do is, if you do find a YouTube video or a course notes or a book and you're finding it hard to follow, try someone else. This is the beauty of the digital age, is we don't spend maybe all of our life savings on a book that we have to wait to come in the mail, and we just have to accept what we have. You have a little bit more freedom to be choosy about who is teaching you these things. So I really recommend, before you commit to paying for a book or paying for a course, go through YouTube and open a few tabs. And even if you just, I don't like the sound of the person's voice, close it, skip it, move on, and see if you can find someone who can describe these things in a way that really click for you and that are meaningful for you. And if you want some recommendations, feel free to reach out. I'm happy to give you my favorite ones. So next week is our third and final quantitative literacy session, and perhaps is the most important one. It's going to be about assessing quantitative research. So whether this is about you assessing your own work, if you're getting ready to submit something, or if you're just reading a journal article and you want to know how much you should trust what you're reading. So we're going to cover the key components that you need to assess when you are reading through quantitative work. I'm going to talk about some of the most common mistakes and weaknesses and issues that can be found in quantitative work, and some best practices that people should follow when they're doing write-ups. I look forward to speaking with you next week. And here's a few more of specific topics we'll be covering: sampling, multiple hypothesis testing, assumption checking, and linear regression assumptions. Until next time, please reach out. Again, here's my email and my Twitter handle if you have any questions. I look forward to seeing you next week. Bye-bye.